So far we have seen two different paradigms of defining languages, one by context-free grammars, and we have defined context-free languages in terms of context-free grammars. That is, the language is called context-free if and only if it is accepted or it is the language of a context-free grammar. We have also introduced a kind of automata called pushdown automata, and we have seen that the pushdown automata are capable of accepting some context-free languages. Today we will see that these two ways of defining languages are exactly the same. That is, given a context-free grammar, I can design a pushdown automaton accepting exactly the same language as the grammar does. And conversely, given a PDA, I can construct a context-free grammar that has the same language as the pushdown automaton accepts. So this involves two constructions, one from CFG to PDA, and the second one PDA to CFG. So I will do these conversions one by one. So let us start with a slightly easier part. Given a context-free grammar, I want to generate a pushdown automaton. This process is fairly intuitive and straightforward. So the input is something like a set of non-terminals, set of terminal symbols, and then you have a set of productions, set of rules, and then you have a start symbol. From that, I will generate a PDA. This PDA is going to have only one state. I may denote this by a star. Of course, the input alphabet is same as this sigma. Gamma I have to define. I will define a little later. A start symbol. In fact, I will use this S as the start symbol. Delta I will define. Definitely this is the only state, and therefore this has to be the start state. And this PDA, converted PDA accepts by emptying its stack. So I do not need to take anything as a final state. Okay. So this PDA accepts by empty stack. So I do not need to have a final state, and of course if I have only one state, making it final is actually not a good idea. Maybe not a good idea. Okay. So I have to define, this is defined, this is defined, this is defined, these are defined. So I have to define this gamma and delta. So for gamma, I will take the union of these two. That is, the stack can consist of terminal and non-terminal symbols. Okay. And then whenever, now I have to think of something like this. Whenever I have a rule of the form, let's say A can be gamma, corresponding to this, I will add the transition delta. Okay. State is always star. I consult nothing from the input and I look at A at the top of the stack. Maybe I write it this way. Okay. Then what I will do, this machine will continue to stay in state star because this is the only state. Instead, it will replace this A by the right side of the production in its stack. So for each rule or production of the input grammar of this form, I will use this. Replace A, the left side of the rule, by the right side in the stack. Okay. And this step does not consume anything from the input. Also, for all A in sigma, sigma is also a symbol in the stack. So I will add this. The state is always star. Consume A. See A at the top of the stack. You simply pop it out. Okay. So using this grammar, if I call it G, I'll generate this PDA. Let us call it M. I leave it to you as a formal exercise to show that the language generated by G is exactly equal to the language accepted by M. So this is an easy exercise. You can show that this is contained in this and this is contained in this. So in either case, you can use induction. But in an example, I will show that this machine M essentially simulates a leftmost derivation of x, of some x in this language. So it's a kind of simulation of leftmost derivation. Okay. So in order to convince that this machine does as intended, let's look at this language. E, or maybe this E can be epsilon or AEB or BEA or EE. So you possibly remember that the language of this grammar, which is the language of the start symbol L as a symbol E, is a set of all W in A comma B star, such that number of A's in W is equal to number of B's in W. Okay. So, given this, how will my PDA look like? This is the start state. For each rule, there are 4 rules. I have to add 4 transitions. This is something like this. First one, E can be epsilon, so consume nothing. And if you see E at the top of the stack, just pop it out. Here also, consume nothing. If you read E from the top of the stack, then you replace that by AEB. Likewise, E replaced by BEA, epsilon, E replaced by EE. Moreover, my input symbols are A and B, so if I consume A and C at the top of the stack, just pop it. Okay, so let us see how it works. So let us look at, let's say, some B, A, B, B, or maybe this is not a good example. Okay, what should I take? Maybe B, A. So there are 3 A's here, 3 B's here, so this is in this language. If I call it L, so this is in L. So if I now look at a leftmost derivation, so I can go like this. There are 2 ways I can apply this rule, BAAB, BA, or I can apply this rule, BEA, AABB, BA. So maybe let me start with which rule? Anything, maybe this one. Okay, E. So with the intention that this first E will generate this one. Okay. So this E will generate BAAB, this E will generate BA. Okay. So now let us see BAAB, or maybe do it this way. Let me first use this. I want to show you the application of all this. Maybe I start with this. So B, A. Well. This is perhaps not a good example. Anyway, let me start with AE. Doesn't matter. So this first E will generate this, the second E will generate this. Okay. So the leftmost derivation, this E, I look at this, I have to use EE. Okay, E. Okay. So this E will generate this E will generate this. Then this is BA, so I can use B, E, A, EE. Then I use the rule, E can be epsilon, so this is BA, EE. Now here I use, let's say, AEB, A. B, A, E can be epsilon, so this I just put it like this, E. Finally, what is the, this is supposed to generate BA, so I use BAAB, BEA, and then E can be epsilon, so I simply write it as BAABBA. This is a leftmost derivation of this thing, this string in the language L. Now let us see what the machine does. So its state is not important, it always remains star. So what I will instead do, let us see how its stack works. So E is the start symbol. Okay. So the machine starts its operation after this. Okay. Then it uses EEE. So it essentially uses this, reads nothing but replaces this E by double E. So it now becomes E. So this is step 1, this is step 1. Here this rule is applied. Then once again the same rule is applied. So this is replaced by E, E, E. This E is replaced by E. Then on this E, I apply the rule BEA. So I replace E by BEA. So now the stack becomes B, E, A, and these two E's are there. Okay, so this is E. Next, this is not a non-terminal symbol, so I apply this rule. If I see B on the top of the stack, I simply consume it. Okay, so this now becomes E, A, E, E. So I have just consumed this E, A, E, E. Then once again I apply the rule B. Oh, okay. Then I apply the rule E can be epsilon. Am I correct? Yes. E can be epsilon. So I apply this rule. E can be epsilon. So this now becomes A, E, E. Again I apply this rule A. Just consume A from the input and push it from the top of the stack. So this now becomes EE. Okay. Then again I apply this rule AEB, right? AEB I write. AEB I apply. So I replace this rule E by AEB. So this now becomes A, E, B, E. Then I consume this A from the input, and at the same time I pop it out from the top of the stack. This now becomes E, B, E. Then I let this E vanish. Okay, so I apply this rule. So this becomes BE. Yep, BE. Then I apply this transition to make it E. Finally, what rule did I apply? BEA. So I make this BEA. Then I apply this transition to consume B from the input, EA. Then E can be empty, this one. So I have this A. Finally I apply this, and this becomes empty stack. Now if I look at the things that I have, this machine reads from the input, this is B, A, B, B, A. Okay. So the string BAA, BBA is accepted because the machine starts with the initial configuration and ends up with an empty stack. Okay. So you see how this stack essentially simulates this leftmost derivation process. Okay. And now you can formally prove that this simulation of the derivation process is perfect in the sense that if we have something in L, this language of this grammar, then there exists a leftmost derivation, and corresponding to that you have a set of sequences, a set of sequence of transitions of this machine that will start with this and end up with this empty stack. Okay, this is fairly straightforward. I leave it to you. Conversely, if this machine accepts some string that corresponds to a leftmost derivation of an element in L. Okay. So this process is fairly straightforward. CFG to PDA. So now let us look at the more complicated thing. Okay. That is, given a PDA, I want to generate a context-free grammar. Now this PDA M, and I eventually want to generate some G. This is my eventual goal. So now I will do something little bit complicated. So this conversion is a two-step process. In the first step, I will convert M to another PDA M prime. Okay, such that this M prime has only one state and therefore it accepts by empty stack. Second, I will convert this M prime to a grammar. Okay, so this is basically the reverse of the CFG to PDA conversion process. Okay, so what does it mean? So if we have something like this, so this step 2, which is actually the easier part. Step 1 is sufficiently more difficult than this, so I will come to step 1 later. So let's consider a transition of the form P A, some stack this, go to state Q and replace that A by some gamma. Okay, but since this M prime has only one state, so this P and Q, they are not actually relevant in this context. They are both star, and since this is an irrelevant information, the rule does not have to take care of this. So for this in delta, introduce the rule A can be A gamma. Okay. So this is consuming A. Of course, A can be epsilon or a real symbol. And you can see that this is essentially a reversing of this previous conversion. Okay. So actually you can think of this. Okay, so consider this A can be A gamma, then consume A. So gamma remains only. Okay. Anyway, whatever it is. So this is a straightforward procedure for converting M prime to G. So I am not illustrating this with an example. This is fairly straightforward. So this is straightforward to prove. the correctness of this procedure. But I have assumed that this M prime has a single state and it accepts by emptying its stack. Okay. So question is such a machine M prime general enough? Okay. So that now leads us to this question. How to convert an arbitrary M to an M prime which has only one state and which accepts by empty stack. In other words, I ask the question, is M prime general enough? In the sense that any PDA with possibly many states can be converted to this form. Okay. So definitely we will now see that this is yes. So that is the most complicated construction of today. So this is step 1, M to M prime. In the last lecture, we have seen that any PDA can be converted to a form, okay, which has, which is of this form, some Q, sigma, gamma, some initial bottom marker, then some transition, there is a start state, and this M accepts both by empty state and empty stack, so and final state. So this is the only final state. And M accepts by both empty stack and final state. So this construction we have already seen, which is essentially based upon the fact that once the machine reaches T, it is capable of emptying its stack at the state T and eventually accept. Okay. So this construction, M, an arbitrary M to this type of M, that is already covered in the last lecture. So here I assume that I am given a PDA of this form. Okay. From these I would like to generate a PDA of only one state, since again this is only one state. The name of the state doesn't matter, so I just call it star. The input alphabet must be the same. Stack I have to change. Listing I also have to change. Delta prime will definitely be different. There will be some start state. Of course, this is only one state, so this is star. And this accepts by empty stack. Okay, one state means having a final state is not really a good idea, so this accepts by empty stack. So M prime accepts by empty stack. Okay. So from this PDA of this particular form, I want to generate a PDA of this form. Okay. Now, this PDA remembers certain things in its stack, in addition to in queue. Okay. So this is also a stack, so I can remember similar things here in this stack. But the state information is apparently lost because there is only one state. So this does not reflect anything on this state. So the idea is that M prime stores the state information of M in its stack. But this has to be done very carefully, otherwise the simulation will not be perfect. Okay. So to that end, what I do, okay, so stores. So how it stores, we will see. Okay, so for that matter, I take gamma prime to be Q cross gamma cross Q. So each element of gamma prime is a state followed by an old stack symbol followed by another state. Okay, so it's a tuple, but I will write it in this fashion. P A Q. Sorry. P A Q. Okay. So I will write it instead of this P A Q. Okay. This means this. And then I will take this equal to the start state of this machine. The start state is S and the last state is T, and the stack symbol is the bottom marker this. Okay, this I will take as the initial bottom marker for this. Okay, so now let me tell what does it really mean when I write PAQ. Okay, definitely you can see that this stack symbol now stores an original stack symbol A alongside two state. So this is the state information that is essentially stored, P and Q. So what does it essentially stand for? So let us look at this. Okay, so let us see M. M has a situation like this. There is something on the stack, but on the top you have A. Okay, and you are in state P. This is for M. Okay, note that this M accepts by emptying its stack. So A will eventually be removed. Okay, so after consuming something like X from the input, there will definitely come a time when this part will not change, only A will vanish, and at that point of time M may be in some state, let us call it Q. Okay, so X is consumed from the input, this part of the stack is kept unchanged, only A is removed. In between you may have replaced A by some other things, the stack possibly grew, but since M accepts by empty stack, if that okay, eventually this has to go, and let's say this happens in a state Q. Okay, correspondingly what happens in M prime, it has its stack consisting of triples. So there is something here, you have this triple P A Q here. You read essentially the same string X and get rid of this symbol. Okay, so this is how M prime simulates M. Starting from P, it can go to state Q, but the only effect on the stack is the removal of this A. Okay, correspondingly, if this M prime has P A Q, it reads the same string X, and the only effect is removal of this. Anyway, the state is here star, state is here star. Okay, this is not an important thing. Okay, so if and only if M has a situation like this, M prime will have a situation like this. So now it says that why this is this, S, this, This says that M starts its operation in state S with only the bottom marker, and after reading the input, it must go to the accept state T with empty stack. So now below this there is nothing, but when we are considering these transitions from this to this configuration to this configuration, we are not changing this part. Okay, so this part is not touched. So it is as if this A is at the bottom of this, bottom and on the top of this stack. Okay, this part is not touched. Here also this part is not touched. Okay, so starting with this initial configuration, start state with these at the top of the stack, it reads X, then it can get rid of this eventually. Okay, and correspondingly, what this is the behavior of M. For M prime, this will be this. It starts with this S, T, and it will read the same string X, and it will be able to get rid of this. So star. Okay. So the big question is, how do I convert transitions of this form to this form? Okay, to a form of M to a form of M prime. Okay, so let us see what we can do for that matter. Suppose that M has a transition of the form B, A, go to state Q. In fact, I can call it Q0 for a reason to be clear soon. And you replace this A by B1, B2, Bk for some k greater than equal to 0. So this belongs to the transition of M. So what does it mean? Okay, it means that M is in state P. It is looking at A at the top of the stack. The first thing it does, it consumes A from the input. A may be a real symbol or epsilon. Okay, so here A can be a real symbol or epsilon. Then what it does, it goes to state Q0, and this is replaced by B1, sorry, Bk minus 1, blah blah blah, up to B1. Okay, so I am eventually interested in when M goes to, so this part is I am not touching. Okay, this is kept constant. I am interested in this part untouched, and this A is just removed. Okay, but definitely A is now replaced with B1, B2, Bk. Then this B1 may be replaced by some C1, C2, Cl, and so on. Okay, but since I am interested from this configuration to this configuration, there must be some point of time when B1 is removed. There must be another point of time after that when B2 is removed, and so on. So the machine reads something like alpha 1, something from the input, and it gets rid of this B1. But B2 through Bk, they are still there. And at that point of time, it may be in state Q1. Then again, it reads something like alpha 2 from the input. it gets rid of that B2. Okay, so this part is unchanged, BK, and B2 is got rid of, so this is B3. And this thing keeps on going. Okay, eventually, after reading alpha K, it gets rid of this BK. So this is state Q2, this is some state QK. Okay. Now this transition says that this next state must be Q0. Q1, Q2, QK, these are for the future. Okay. So first of all, I take X to A, alpha 1, alpha 2, alpha K. Moreover, M prime can guess. So M prime guesses. So this transition only gives Q0, but Q1, Q2, QK, it doesn't know. So it guesses Q1, Q2, QK over the set of all possibilities. Okay. Therefore, if I have to convert this to a transition of the form of M prime, it will look like this. It will first consume A. So from P, you have to go to QK. State is not important. A is consumed from the input. From P, you get rid of this A and go to QK. And what will be there? State will be same as this. But because this B1, B2 is there, so you guess Q1. Okay, no, this is Q0. Then Q0 is coming from this. Then for some guess, get rid of B1, go to Q1. Then from Q1, you get rid of B2 by going to some state Q2, and so on. Likewise, QK minus 1, get rid of BK, we end up in QK. Okay. Maybe another. Okay. Now, for each transition of AM of this form, I will introduce all possible transitions of this form. Okay. For all possible guesses of Q1 through QK. If any guess succeeds, okay, then what will M prime do? It will be able to get rid of B1 by going to some state, some guessed state. It will be able to get rid of B2. Okay. So this is essentially, okay, Q1. And then it will be able to get rid of B3 and so on. It will be finally able to get rid of BK. And eventually reach this state QK. So PA, QK. So the overall effect is the getting rid of A and moving from P to QK. And since M prime can non-deterministically guess what the states will be, it will do it for all possibilities of Q1 through QK. Okay, so this is a little bit of complicated construction. So I would like to explain this in view of an example, and I believe the example, I have this example already here. So let us consider the state of the set of all strings over a comma b of the form a power n, b power n, n greater than equal to 0. Okay. Now we have seen a PDF for this. Okay. This has two states. Okay. For every a, so it starts with this bottom marker at the top or bottom of the symbol, and then it replaces in this state S, which is the start state, replaces each, okay, for each A, it essentially pushes one capital A. Okay. Then when the input consisting of A's, okay, the part of the input consisting of A's is read, it does not hamper the stack, simply moves to the state T. And at T, for each B consumed from the input, it pops one A. Eventually, when all B's are consumed, it pops out this bottom marker. So this machine is of that particular form. It has only one accept state T, only one final state T, and it accepts by going to this state and also by clearing its stack. Okay. So now let us look at the converted machine. So this is the only state star. There will be transitions of this form. Now if you have something like this, maybe let's say S, A, S. What does it say? This machine starts at S, sees an A at the top of the stack, eventually ends up in the same state S, but with that A removed. Okay. But if you look at this, in the state S, nothing is popped from the stack. It's only pushed. Okay. So states like this, you end up in S, okay, after removal of something. So these are actually useless stack symbols. This will not take part in the working of this machine or this machine. Okay. Therefore, I can get rid of this S, T, A, S, and T, this S. Okay. In fact, you also see that from T, you can never end up in S. Okay. So these are useless. Okay. So when you mechanically use this construction as mentioned earlier, you should use these symbols. But in the current context, you can see, since I am doing it as a human endeavor, you can see that these are useless symbols. You cannot end up in S after decreasing after popping something from the stack. Okay. So all pops have to be in T, and therefore these four are the relevant members of gamma prime. S bottom marker T, S A T, T bottom marker T, and T A T. Okay. Now let us look at this S A this. Okay. So what does it say? The machine is in state S. It reads this and replaces that by this. But eventually I want, this is capital A after consuming one A. Okay. Then eventually I have to get rid of this A. I have to get rid of this also. Okay. So at some point of time, this must be like this. And after that, this must be like this. Okay. So here I know the state is S. Okay. This can be either S or T. This can be either S or T. But once again, if I make I would say a human judgment, I can see this cannot be S. Because in S, there cannot be any pop from the stack. So it has to be T. Okay, so in an actual construction, you actually add for both non-deterministic choices S and T. But here we can see that if we have S here, this is a bad thing. Okay. So you read something here and eventually get rid of this A. But at that point of time, you cannot be in state S. It has to be in state T. Eventually, you also get rid of this. Okay. So that means S for this. Okay. So I have, So I am starting with S. Okay, I have these on the top of the stack. I will eventually reach T. Okay, for that, the first thing I do is I am reading A. Okay, so that is what is given here. I am reading A, consuming A, and then from S, somehow I have to go to T after consuming this A from the stack. And from this to this, I have to go, from T to T, I have to go after consuming this. So for this, I am adding this. Likewise, if I have SAA, so instead of this, I have A here. So I have a situation like this. Let me just, somewhere it is something there, and then I have A. Then this A is replaced by AA. Eventually, this machine will get rid of this A, which means it will get rid of this A first, and then it will get rid of this A, second A. Okay, leaving this part untouched. And once again, from here S to S, and here it cannot be S once again, because after popping something you can never reach S, so this has to be T. Okay, so this means you this should be small a. This should be small a. You consume A. Okay, then you replace. You want to get rid of this capital A. Okay, so but that is replaced by AA. So the first A can be removed by going from S to T. The second one remove going from T to T. Okay. So this way, if you just work out all these things, this gives this, 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 and finally this gives this. Okay. So let me just simplify this machine. So you see here, so all these T's are in the stack, so this is not relevant. So I will use this S and bottom marker, and I will write it as this. This as, this as A sub S, A sub T, and this sub T. This is always T, so it doesn't matter. I do not have to remember this. Okay. So I can simplify this machine as follows. Okay. So now my gamma is just this, and this. Okay. And this is the only state. What will be my transitions? Read A. If this is there, replace it by this, so that this will be removed by the state T. You read AS, replaced by ASAT. Okay. Then there is a jump from this to the state T. So essentially you convert this to this, and or if it is AS, you will go to AT. And what will you do in state T? Read B, T, epsilon, B. Do not read anything. Eventual cleaning, this can be epsilon. Okay. So let us see what happens, this is the last example, what happens if the input is A, A, B, B. Okay. So these are just shorthand notations for that triple. Okay. And I have got rid of that T because that appears everywhere. Okay. So let's see. So this step is initialized to this S. Then one A is consumed. This rule applies. This rule applies. Sorry, I should have an one AS here. Okay. So after consuming an A, this becomes T for removal by this. Again, another A is read. So AS, A. This AS changes to AT. Okay. But a new AS appears here. Then two A's are consumed. Now there is a necessity to convert, to go from that earlier state S to state T. So I will use this AS AT. So this becomes epsilon bottom T AT AT. Then you are effectively in state T. Okay. This is the right side. This is the left side of the triple. Then one by one you consume two B's, get rid of these ATs. Consume another B, get rid of this. Sorry, we got rid of. And then you did epsilon, get rid of the final this bottom marker. Okay. So A, epsilon, B, epsilon. Okay. Yeah, so this example illustrates how this construction of PDA to PTA to a PDA of only one state works. So the formal proves that the language of M or M prime is the language of M. It is intuitively clear for us, but it requires a formal proof, and for that you can anyway go by induction on the number of steps of this transition. Here 1, 2, 3, 4, 5, 6. So 6 transitions. So use something like that. Okay. For example, if you have from the start symbol. Okay, so it's something like this. You have some A, read X, and with an empty stack. In M, if and only if, and then anyway, this is basically the same thing. PQ. This is P, this is Q. Then you read the same string X, and you have PAQ, end up with an empty stack. If this thing happens in M, this thing will happen in M prime, and if this thing happens in M prime, this thing will happen in M. So that will essentially prove that they have the same language. So you can use induction on the number of steps in the transition function. Okay. In any case, this is not a very easy construct, but at least this shows that CFG and PDA are equivalent. Okay, so it's already past 1 hour, so let me stop. The next class, we will look at something called deterministic pushdown automata and the corresponding deterministic context-free languages. Okay, see you.